So here is how Ian Goodfellow defines deep learning. The idea is to allow computers to learn from experience and understand the world in terms of a hierarchy of concepts, with each concept defined through its relation to simpler concepts. All deep neural networks try to break down information and representation into hierarchical information or into hierarchies. So, the hierarchy of concepts enables the computer to learn complicated concepts by building them out of simpler ones, right? So, hierarchical information, hierarchical representation of features, hierarchical understanding of concepts helps the computer to simplify things. If we draw a graph showing how these concepts are built on top of each other, the graph is deep with many layers. And what is efficient is when we can learn these representations. Mapping representation to the output answer is not the most efficient idea. But what if we could learn the representation and the computer could produce its own representation of the car that it can learn itself and then come up with an output. So this approach is also known as representation learning. So his argument. So another perspective on deep learning is that depth enables the computer to learn a multi-step computer program, right? So till now we have been talking at an abstract level, which is representation. Now we're going one level below, where we're talking about depth of the neural networks, right? And we are kind of favoring the idea of depth. Each layer of the representation can be thought of as the state of the computer's memory after executing another set of instructions in parallel, right? Actually, networks, deep neural networks with greater depth can execute more instructions in sequence. We know. So the largest umbrella is the AI umbrella, right? So one of the examples that he gives in the AI umbrella is the knowledge base. Then underneath the AI umbrella is machine learning umbrella. So then there the example is the classical machine learning algorithms, for example, logistic regression. Then we have one level beneath it is representation learning, right? For example, shallow encoders, shallow autoencoders. Then we have something which is known as deep learning. One of the example in deep learning is the deep neural networks multi-layer perceptron. Now, he says that another crowning achievement of deep learning is its extension to the domain of reinforcement learning. In the context of reinforcement learning, an autonomous agent must learn to perform a task by trial and error.
We have discussed the idea of attention a lot, right? But we have never discussed the idea of cross attention. So one of the architecture that we keep on emphasizing is the encoder decoder architecture. This encoder decoder architecture is mentioned in the paper known as attention is all you need. When we say that encoder has 6 layers, we simply mean input is processed through these 6 identical structures, through these 6 identical layers, and it is always in a serial chain, right? Now to bridge the gap between an encoder and a decoder, we have something known as cross attention. Now, why do we call it cross attention? We call it cross attention because it takes the input or the source of the attention's input is the encoder. So, query is coming from the decoder. We can see here, let's pay a little attention. So we know every attention matrix is going to have its own key, query, and value, right? So the query comes from the decoder. The key, which is K, comes from the encoder. And the value is also coming from the encoder. So the decoder is currently trying to generate the next word in the target language. Let's say the target language for this paper is French, right? So query is basically saying, I am currently at position I in the French sentence. What information should I be looking for? Key from encoder says, here is the map of all the concepts in English source sentences, right? Whereas value says, and here are the actual semantic context or semantic content of these particular concepts, right? So query is coming from decoder and key and value both are coming from encoder, which is from the above stack. So if we, look at them from top to bottom, key and value are coming from the above stack and query is coming from the decoder itself. So the only idea in cross attention is that they are paying attention to what is coming from the encoder, right? And the source of information has changed. For the decoder only stack or for self attention, we did not have, this cross stack exchange of information. They simply looked at the embeddings. Now, embedding vector was a combination of token embeddings and positional embeddings, right? So it looked at that combination. That's it. But when it comes to cross attention is looking at the encoder stack, right? It's taking some information from the encoder, it's having some of information of its own, right? Now, why are we doing this, right? So why do we need to do this particular thing? So if we don't do this, if we don't have something like a cross attention, the decoder would be blind to the source sentence.
I have been hearing Jensen, the NVIDIA CEO, talk about AI as a five-layer cake. He keeps on saying that there are multiple nuances to AI. So the first layer in AI, so just imagine that we are going to break down AI into multiple layers. So this video is going to help us understand which nation among US and China has better competitive advantage across which layer. So the first layer we are going to talk about is the energy layer, right? So we know that every GPU, let's say all foundational models are run on GPU. So China produces something around 9,300 to 10,000 total watt hours. Similarly, US is halfway there. It's 4,400. Right? Now the second layer, which is the chips layer or the chip layer, we know that Nvidia dominates the chip world and US kind of has a competitive advantage here. But how? So there are two ways to manufacture these kind of chips. So one is the EUV technology, and then the second is the DUV technology, as mentioned here. So EUV is like the proprietary or the most gold standard one for producing these leading edge chips. But the problem is, due to trade restrictions, China cannot use this particular technology. China has to rely on something like a DUV, which is deep ultraviolet. So this particular DUV strategy requires the Chinese chip manufacturers to do a computation four times, right? So it has very low precision and very reduced efficiency. Now let's go back to the next layer, which is the infrastructure layer. So here I will talk about one performance indicator, which is the velocity. So the strategy for China here is definitely helping China win because the velocity, it creates more and more velocity gap, right? Whereas in case of US, the cost is also very high. The power cost is significantly high as compared to Chinese facilities. In China, it only takes 3 cents per kilowatt hour power cost, but in the US, the cost might be 4x higher. Now let's talk about the most important layer, which is the most commonly heard of, the model layer, where we have all the models lying with these particular countries. Before, the cost for DeepSeek V3 was $6 million, whereas the US frontier model costed hundreds of millions of dollars. Now let's talk about the application layer, which is the last layer. So we can have two perspectives to view this particular race. One is the marathon and one is the sprint. There is one particular phase which is very explosive, very time intensive, very compute intensive, which is known as the training phase, where the model tries to learn. What does the model tries to learn? Model tries to learn the data, right? Model tries to learn the representation, the features in the underlying data, and then model produces some weights, and the weights are learned and the weights are saved, right? Then what happens is we freeze the model. Between the training phase and between the inference phase, the model weights do not change. After training, we freeze the model weights. Right? In case of humans, the concept of freezing the weights is not true. Right? So humans continuously learn while operating in the world, right? Like an agent. So the fundamental intuition of a biological brain is it does not freeze my model weights, it does not freeze my neurons. Now, what does continual learning say? Continual learning says that what if I could continually learn lifelong from my environment, right? Across multiple tasks. I perform task A, right? And then I learn something, and I perform task B after task A, then I learn something else, right? But what really happens in those? I mean, what are the challenges? So there are multiple challenges that can happen in case of continual learning, right? So continual learning basically means here that instead of traditional learning, or after the traditional learning is over, I am getting to perform task A, I will learn something from that. I am getting to perform task B, I will learn something from that, and task C and task D. As I move or in order in time, in the time dimension, I will keep on learning new things, I will keep on accumulating my new knowledge, right? I will not freeze my weights permanently. What are the challenges in case of continual learning? So one of the challenges that generally happens is catastrophic forgetting. Once we try to learn task B, the neural networks overrides the useful weights that were needed for task A, right? So new learning kinds of overrides the old learning in the previous sequence, right? Previous task performance degrades significantly. This is what happens. This is what basically is meant by catastrophic forgetting. Now, in what is stability plasticity dilemma, right? So this is also a very famous very famous word, that stability plasticity dilemma. So what really happens is, I mean, here too plastic means we are forgetting the old knowledge, and too stable means we cannot learn the new knowledge, right? So if we have high plasticity, which is too much plastic, then we tend to forget the older knowledge. We don't learn fast. Forgetting is more common. Whereas if we are too stable, we cannot retain or remember the new knowledge. The learning gets slow. But now, what are the techniques that we generally, we use as engineers to simulate something like continual learning? So one of them is EWC, which is elastic weight consolidation. So what really happens in this particular technique is, we estimate which weights are really important for previous task, right, and penalize changing them so that they don't completely change. But this also does not scale really well, with a lot of tasks, right? So the main idea is that we don't have to change a lot of important weights too much, right? So this technique was known as elastic weight consolidation. Now we have one more technique, which is replay based methods, right? So which is also known as memory replay. So the idea here is that we retrain on old data while learning new data, right? So it's like we might have two versions. One is we're storing a lot of old samples with a memory buffer, and second is we are using a generative model to recreate the past data, right? This might mimic how humans rehearse and rehearse memories. So but the problem is that we have memory which is very expensive, right? Memory and compute, definitely both of them are very expensive. So this has its own challenges. Now the third architecture, or the third idea, is that why don't we mutate the architecture? Why don't we do something on the architecture? We have tried playing around with the weights, we have tried playing around with the memory. Now what about if we play around with the architecture? So the idea is add new neurons, or maybe new sub-neural networks for newer tasks. As we see newer tasks in the sequence, why don't we add new neurons and new subnetworks in the architecture? What about the large foundational models? What do these kind of models do today to simulate continual learning? Instead of changing the weights per user interaction, they store new information in a database, which we very commonly call as a vector database. Then they retrieve the relevant information at inference time, at query time, not during training time, and then they inject that particular information into the context window. So the model might appear or behave as if it has learned, but the weights always stay frozen. We know that why it has not been fully solved. First thing is, it's very expensive. Why it's very expensive? Because we cannot mutate all the weights all the time at every user interaction every day, right? And there are challenges like catastrophic forgetting that we saw. There are challenges around stability and plasticity. Then there are challenges around memory. If we are able to have a breakthrough in case of continual learning in this particular area, then that would be one step closer to having a super intelligence, having artificial general intelligence system. What the hell is a world model? They are not only large language models, they have physical and spatial understanding of the world. It knows that if you push the glass off a table, it's going to fall. That means they understand the idea of gravity. So Gemini 3 holds a record of performing 84 to 85% on that AGI-2 benchmark. So in its deep thinking mode, Gemini 3 has achieved gold medal standards in the International Physics Olympiad. Gemini 3 does not translate images into text to understand those images. It basically processes video, audio, and spatial data in a unified latent space. The first level of all of these AI systems are nothing but the transformers, whereas level 3 is what I would define AGI using my taxonomy, which is inspired by DeepMind. So now level 3's AGI is nothing but it can generalize the world models across every possible domain. Now level 4 is superintelligence, where you simulate the world faster and more accurately than reality in itself.